Hello friends. So in the previous video we have actually derived the starting torque equation of the single phase induction motor, right? So for an induction motor where you introduce something which is called an auxiliary winding, so this is the starting torque equation, and in this equation you could see that you should make sure that theta, which is the angle between Im and Ia, should not be equal to 0, right? That means what I am trying to tell here is that this ZA and Zm, that is the total impedance of the auxiliary winding, the total impedance of the main winding should be such a way that they have a phase difference like this. They should have a phase difference. For example, this is the voltage phasor, so Im should be somewhere here like this, and Ia can be somewhere like this. So this is your theta A, this is your theta M. The angle between these two is theta. So in this case, in this particular case, this is equal, theta is equal to theta M minus theta A. Now, based on how we do this, there are lot of types of induction motors. Out of that, the first one that we are going to discuss today is called the resistance split phase. Resistance split phase induction motor. Resistance split phase induction motor. I already told you, see, all the single phase induction motors are given a single supply. That is, from the same single phase supply, you are exciting both the auxiliary winding as well as the main winding. And once the motor gets enough speed, say 70 to 80% of its rated speed, you cut off this auxiliary winding using a centrifugal switch. So once the motor reaches a particular speed, that switch cuts off the auxiliary winding. We have already seen those things in the previous classes. So in a resistance split phase induction motor, you see this angle theta A, this ZA. Okay, so ultimately see there is an impedance triangle for this, right? So for example, the auxiliary winding, it will have an impedance triangle like this. So this is RA, this is XA, and this is your ZA, and this is the angle theta A, right? And then for the Zm, there is the main winding, this is the auxiliary winding. And for the main winding also, you can have an impedance triangle. So this is your Rm, this is your Xm, this is your Zm, and this is theta. So if you see, ultimately this theta A is equal to tan inverse of Xa divided by Ra, right? And theta m will be equal to tan inverse of Xm divided by Rm, right? So only if Xa divided by Ra is equal to Xm divided by Rm, theta A will be equal to theta M, right? If Xa divided by Ra in the sense the total resistance of the auxiliary winding is equal to Xm divided by Rm, that means theta A will be equal to theta M. But we don't want this condition, right? So what we want Xa divided by Ra should not be equal to Xm divided by Rm. Xm divided by Rm. So what we do is that we either make so now here we have to make a choice, right? See, the main winding you see here, that is going to be there throughout the working of the machine, right? That is going to be there throughout the working of the machine. So we have to select a resistance between these two. See, Ra can be greater than Rm or Ra can be less than Rm. These are the two conditions possible. So see, Ra is a resistance which is only present during the starting. Ra is the resistance of the auxiliary winding. It is only present during the starting, right? So Ra is only present during starting, right? And Rm is present throughout the working of the machine. So which should have less resistance? Naturally, Rm should have less resistance, right? So less resistance means, that means we will write it here, that means Rm should have less resistance as compared to Ra. Less resistance how will you get? If you use thicker wires, right? So Rm will be less than Ra, that means Rm will be made using thick wires, right? If you want, you can make Ra also less resistance. It is not anything that you should make Ra high resistance, but then you have to use thick wires which is comparatively more expensive as comparatively using thin wires. So RA, you see, RA is greater than RL. So for making RA, you use thin wires as opposition to RM, which is usually made up of thick wires actually. And another thing which is important here is that, so this is one condition about the resistance of the winding. See, and ultimately what do you want? Our objective is to try to find when you will get torque starting to be maximum, right? So in this case, what we will do, we are putting resistance to the auxiliary winding. So at what particular resistance value you will get maximum starting torque? That is what we are trying to say here. What resistance condition we are getting maximum starting torque? So that is what we have to see. So to find that maximum condition, we have to draw the phasor diagram of this particular circuit. So what do we have information now? So this is your rotor of the induction motor, and this is your I have to bring it a little bit down here. Yeah. So this is your auxiliary winding. This is your auxiliary winding, and here you are having, for example, a variable resistance. You are having your variable resistance here. So we will call this as R external, and the auxiliary winding, let it have a resistance RA. Okay, so the total resistance of the circuit is now RA plus R external. Okay, then you are having your main winding here, your main winding. This current is IM, this current is IA, and these two are connected in parallel to the same supply V. Okay, that I am not showing here now. So now we have to draw the phasor diagram, right? Now we have to draw the phasor diagram. So what are we actually trying to draw? Now I have already explained how to draw the circle diagram. If you have not watched this video, please go and watch the basics of circle diagram, which I have already covered in induction motors, 3-phase induction motors. We will be using some concepts from there. So what we are going to draw is the variation, or we can call it locus of IA with respect to changes in RA plus R external. That means when R external, you are going to vary it from one value to different value. So with the changes in value of RA plus R external, that is from RA plus R external 0 to RA plus R external to infinity, we are going to see the variation. Okay, so that is the basic idea. So here you are having, this is RA plus JXA, RA plus JXA, and this is RM plus JXA. Right. So first we will draw the voltage phasor as usual, voltage phasor, and see, we will just draw the value of IM. Okay, the value of IM, for example, it is something like this. So this is IM, and this angle is theta m. So this part of the circuit is over. This is Zm, this is Zm angle theta m. So this is over. Now we have to draw for this particular part here. So first, when RA plus R external is equal to 0, when RA plus R external is equal to 0, what will be the current? If RA plus R external is equal to 0, the value of IA will be equal to V divided by XA, right? V divided by XA. When the total, for the total impedance of this circuit, Z will be equal to RA plus R external plus JXA, right? So if RA plus R external is equal to 0, IA will be equal to V divided by XA, right? V divided by XA. So this is ideal inductive circuit. So I am just going through the basics of circle diagram actually. So this will be that axis. Current will be 90° lagging. So this is the position where RA plus R external is equal to 0. Okay, and this value will be equal to V divided by XA. I am strongly recommending you go and watch that video once again. And if you see, as R external you are increasing, as you are increasing the value, the resistive nature of the circuit increases, right? The resistive nature of the circuit increases, and if it increases to a very high value, the current will go to 0. The current will go to 0, right? And it will be a pure resistive circuit. So the locus will be something like this. It will be like a semicircle. So we have already discussed this. I am going to not discuss this once again. So this is the locus of IA when RA plus R external changes from 0 to a maximum value, or we can call it as a very high value. Okay, so this is the condition. So this is the locus. Now what we want to do, I already told you the torque starting is equal to 2 into R2 into Im into Ia into sin theta. And it is very tempting to tell this torque starting will be maximum when theta is equal to 90 degree. Torque starting is 0 when theta is equal to 0, and it is very tempting to tell that the torque starting will be maximum when theta equal to 90 degree, but that is not the case. I want you to think about that. Why at theta equal to 90 it may not be maximum? Okay, I want you to think about that. Actually, it is not theta equal to 90 degree which is maximum. It is Ia sin theta should be maximum. Ia sin theta should be maximum for the torque starting to be maximum. Torque starting to. So, from this locus of Ia, we have to find that value of Ia where Ia sin theta is equal to maximum. That is the important point here, right? So, how do we do that? So, for that a simple technique is there. It is basically a geometric technique actually. So, what we have to do is that you have to take the center point of this value. This V divided by Xi is the diameter of this particular semicircle, right? This is the diameter of the semicircle, and this is a chord. Okay. So, now if you draw a line from here perpendicular to this line, perpendicular to Im, perpendicular to the chord, okay. So, this is 90 degree. Now, this goes and intersects at this particular point, right? This goes and intersects at this particular point. Let us call it as OA. Okay, we got this O, and this is point A. Now, that point, this point here, this line OA will be that value of Ia where, now where is this is, now this is OA, right? And the angle, this is the Ia value. This semicircle is the various values of Ia. From that you have found out one particular value of Ia. So, the angle between OA and this Im will be angle theta, right? Now, with this procedure that we have done, this is the value of Ia, that is OA is that value of Ia from this total locus where this Ia sin theta will be maximum, right? Now, what is OA, what is this value? This value is the sin theta, right? This is OA sin theta. This is OA sin theta. OA sin theta will be maximum. Okay, OA sin theta will be maximum. So, what is OA? OA is the value of Ia where Ia sin theta is maximum. This has nothing to do with electrical engineering. It is basically a simple geometric technique. For any other value of Ia, that is for example here, etc., you will not get the maximum value of Ia sin theta. So, only by this procedure, that is taking the center, drawing a line perpendicular to this Im value, and where it intersects this semicircle, that value of Ia will give maximum Ia sin theta value. Okay, that value will give maximum Ia sin theta value here. So, now that is all okay, but now we have to do some more analysis here. Okay. So, this is the basic procedure. So, we will take the diagram to the next page so that we can do a small derivation here. Okay. So, now we will do a small derivation. Now, what we are going to do is that we will just mark all the angles. So, this angle between V and Im is theta m, and the angle between V and OA, which is the Ia value, that is theta a. Right? That is theta a. So, the angle between the angle theta, which is the angle between OA and Im, I will call it as Ia here. Okay, the angle between Ia and Im is theta, right? So, that theta is equal to clearly theta m minus theta a. Theta m minus theta a. Now, see, there is an interesting thing here. Now, if you join this, now in this triangle OAB, this line OA will be equal to AB. It is simple geometry. We are drawing this perpendicular line from here. So, in triangle OAB, OA is equal to AB. OA is equal to AB. That means this angle AOB will be equal to angle ABO. These two sides are equal, right? So, this angle will be equal to this particular angle here. This angle and this angle will be exactly the same. Okay. Now, if you use a little bit of mathematics here, you can find that if this angle is theta a, this angle also will be theta A. That is, angle ABO will be also equal to theta A. Now, what is angle AOB? Angle AOB is theta. So, theta will be equal to theta A. This angle is theta, this angle is theta A, that will be equal to theta A, that is what I mean. But we know that theta A is equal to theta M minus theta A. So, theta M minus theta A is equal to theta A. So, in resistance split phase induction motors, the condition that you have to remember is 2 theta A is equal to theta M. This is a very important relation. So, that is an interesting relation that we have got here now, that is 2 theta A is equal to theta M, or I can tell theta A is equal to theta M by 2. You must not forget what is this theta A and theta M. Theta A is the power factor angle of the auxiliary winding, theta M is the power factor angle of the main winding. So, we will take tan on both sides. So, tan theta A is equal to tan theta M divided by 2. Now, with a simple geometric relation, I can write tan theta M by 2 will be equal to sin theta M divided by 1 plus cos theta M. Okay, this is tan theta A. And what is tan theta A? Tan theta A is nothing but what? See, this is the impedance triangle, right? So, this is theta A, and this resistance is RA plus R external, and this is XA, and theta M, this is theta M, this is RM, and this is XA, right? Tan theta A will be equal to opposite side by adjacent side, right? So, XA divided by RA plus R external will be equal to sin theta M. Sin theta M will be equal to opposite by hypotenuse. So, XM divided by ZM divided by 1 plus cos theta M, that is RM divided by ZM. RM divided by ZM. So, if I further simplify it, I will get XA divided by RA plus R external is equal to XM divided by ZM plus RM. ZM plus RM. So, if somebody asks you at what resistance external, what amount of R external should I add to a given single phase induction motor? See, for a given single phase induction motor, RA, XA, RM and XM will be given nameplate ratings, right? Simple nameplate ratings. So, at what R external value you will get maximum torque at the starting condition. If somebody asks you this question, you have to just use this relation here, right? So, this equation, if you want, we can simplify a little bit more, but I don't think it is necessary. All you have to actually remember is this particular condition here. Once you remember this particular condition, rest all easily you can solve mathematically. Okay, just remember this particular condition, that is 2 theta A will be equal to theta M, and this is the condition where Ia sin theta is equal to maximum. That implies torque starting will be equal to maximum. Okay. So, with this, let us conclude this video. I think I have told a lot in this video. So, what we saw today is that the resistance split phase induction motor. So, in resistance split phase induction motor, you are adding an external resistance to the auxiliary winding to maximize its starting torque, or in general to just start the induction motor. So, then we saw what is the condition of maximum torque. We saw that the maximum starting torque is obtained when Ia sin theta is equal to maximum. So, for that we did this small derivation here, and we found out that when Ia sin theta is equal to maximum, that is when Ia sin theta is equal to maximum, 2 theta M is equal to 2 theta A is equal to theta M. Okay. So, when Ia sin theta is equal to maximum, torque starting is equal to maximum, and at that condition 2 theta A is equal to theta M. Okay. So, with this particular relation, you can easily find what is the external resistance that you have to add to get maximum torque. So, I will conclude today's video. I hope you have understood the topics. If you are having any doubts, please put them in the comments in the video below. And please remember, we are fighting against this coronavirus in this lockdown. So, please do your part to break the chain. So, till I see in the next video, it's me Varun signing off, and have a great day.